Okay, we're going to take a look at one of the most important principles in physics, and that's the conservation of linear momentum. Say linear momentum as opposed to angular momentum, two different sorts of momentum. We're looking at momentum of bodies moving in a straight line, and we're going to get some amazing results about how various values are conserved. So let's start by considering two masses, A and B. And to make things simple, I'm going to assume they're both circular or spheres, like billiard balls or marbles. And to begin with, they're both moving with their own velocity from left to right. So ball A is moving from left to right, like this, and we'll say that it has a velocity u of A. And sphere B is also moving from left to right, and let's say its velocity is ub. Now if ub is bigger than ua, ball A is never going to hit ball B, but if ub is less than ua, then they'll collide. And it's that collision that I want to consider now. Let's also assume that ball A has a mass m of A and ball B has a mass m of B. So if these two balls are in motion and the red ball is going faster than the green ball, they're going to collide after a certain amount of time. Let's have a look at what happens at the collision. So when both balls are touching each other, the physics and dynamics of what's going on is very complicated. But what we do know is that the force exerted by ball A on to ball B, let's call that F of B, is equal and opposite to the force on ball A imparted from ball B. Newton's third law, equal and opposite forces. So these two balls will be in contact for a very short period of time, and momentum's exchanged, energy may be lost, and we know that each ball imparts an impulse on each other ball. Should be minus there. And we know that impulse is really, if the force is constant, just the force times the time. So each ball experiences an impulse from the other ball, where t would normally be quite a short space of time. Something like, imagine a cricket ball hitting a cricket bat, or a baseball hitting a baseball bat, or a footballer kicking a football. T would be very short, but the force would be quite large. And then once this collision has taken place, ball A and ball B will have different velocities. Let's say ball A moves away with a velocity v of A, and ball B moves away with a velocity v of B. Now, depending on the initial speeds, v of A and v of B could be in opposite directions. Now, returning to the collision, what we know is that minus F of A is equal to F of B. This is just Newton's third law, equal and opposite forces. But we also know from Newton's second law that F is equal to mass times the acceleration. In other words, if we have a mass and we impart a force on it, it will accelerate. So this just implies that minus ma times the acceleration of A equals mb times the acceleration of B. And in fact, because they're both in contact for the same amount of time, I can multiply both sides by t to get that equality. And this is essentially just equating the impulse of A and B to the impulse of B on A. The minus sign is there because it's in an opposite direction. Okay, let's make a little bit of room here for some more maths. Okay, so we've got that relationship. Now we also know from our one-dimensional kinematics that velocity equals starting velocity plus at if acceleration is constant. This is all happening very quickly. We're going to assume the acceleration is constant here. I can rearrange this to say at equals the differences in the velocities, and if I then use this relationship in here to get rid of t, I'll find minus ma, and I can substitute the at term in, which will be va minus ua equals the same for the right hand side, m of b vb take away ub, that should be. And I can rearrange the whole lot, make it neater. I end up with ma ua plus mb ub equals ma va plus m b v b. Now let's take a look at what this is telling us. This term here is simply the momentum of A before the collision. And this term here is simply the momentum of B before the collision. So this left hand side is the momentum of the whole system before the collision takes place. And on the right hand side of the equal sign, MAVA is the momentum of A after the collision, and MBVB is the momentum of B after the collision. So the right hand side is the total momentum after the collision. So you can see that the momentum of the whole system before the collision is the same as the momentum of the whole system after the collision. I'm saying the whole system being just these two balls. There's nothing else acting on them. There's no air resistance, there's no external force. The only forces that are present in this calculation are when the balls collide, and we're making the assumption they collide for a very short length of time and everything's symmetrical, the balls are the same radius, the same, there's no friction involved, and it's quite a good approximation. But it's a very powerful result, this, and it's the conservation of momentum. So when two balls collide like this, momentum before equals momentum after. And using that fact is going to help us solve problems to do with colliding objects in a game. It's going to be an approximation, but it's going to work for most situations unless we have odd-shaped objects moving through liquids, moving under the action of an external force. But if things are just moving, we can approximate them as particles perhaps, or spheres. The conservation of momentum will apply, and it will help us work out the dynamic and the trajectory of objects.